In this example, we're asked to determine whether this series is convergent or divergent. This is in the section on alternating series, but at first glance it's not clear that this is an alternating series at all. So what we can do is we can start plugging in values for n and just writing out, I'll write these in blue. Just when n is 1, this is 1 over 2 to the 1 times the cosine of pi. When n is 2, this is 2 over 2 to the 2 times the cosine of 2 pi. When n is 3, this is 3 over 2 cubed times the cosine of 3 pi. Okay, and then I'm out of room here. This is poor planning. Let's plug in at least one or two more terms here. So 4 over 2 to the 4. This is supposed to be a plus sign. So we're adding the next term 4 plus 2 over 2 to the 4 times cosine of 4 pi. And this is probably enough, so let's see what happens here. As we start to work these out, all these numbers we can just leave as they are, but let's take a closer look at these cosine values. These cosine values are multiples of pi, so cosine of pi is a negative 1, so this is actually negative 1 over 2 to the 1. Cosine of 2 pi is 1 though, so this becomes plus 2 over 2 squared. And same thing now, so we can see what's happening. The cosine is alternating between negative 1 and 1. Cosine of 3 pi is another minus 1. So minus 3 over 2 to the third, plus 4 over 2 to the fourth, minus plus, and now we see a pattern. And so actually, this series is just kind of fancy, right? This series is just a fancy way to write the alternating series. Sum n goes from 1 to infinity. Negative 1 to the n times n over 2 to the n. Okay, these series are exactly the same. Remember, we talked about in a previous note section that the representation of a sequence is not unique. You can get the same sequence by many different formulas, and this is an example of that. Okay, but now that we see that this is alternating looking, that this is the sum 1 to infinity, negative 1 to the n times some sequence here, which we'll call b sub n, then we can try to apply the alternating series test, and to do that we just have to look at this term right here, right? Okay, so let's take a closer look then. Our b sub n for this potentially alternating series is n over 2 to the n. This is of course positive for all n greater than or equal to 1, and so that's checked off. The next question is this decreasing? Okay. And you might be able to make a nice guess. You know, we've talked about exponential functions and how fast they grow in previous chapters of this class. But let's take a look at this. So what we can do now is we want to know, is this decreasing, or at least decreasing eventually for large values of n? What we can do is use calculus. This is a calculus class, right? So we can replace our series, our sequence here, our b sub n, we can replace this by a function, call it f of x equals x over 2 to the x. So just replace it by a function where the values of x can be any real number as opposed to just the whole numbers that we get from a sequence. And then remember, when you have a function like this and you're able to take the derivative, so a differentiable function, then this function itself is decreasing if its derivative is negative. So I'll say if and only if, but if f prime of x is less than 0. That's what it means to be decreasing. So we can use calculus to help us compute this. So let's do it, right? This is a quotient, so we need a quotient rule to compute the derivative. And the quotient rule is just 2 to the x minus, so remember the quotient rule is bottom times derivative of the top minus the top times the derivative of the bottom. And the derivative of 2 to the x is the natural log of 2 times 2 to the x. And then this whole thing is divided by the denominator squared. And what we're going to do is kind of factor this thing and take a closer look at what's going on here. So log of 2, natural log of 2 is a constant. 2 to the x is a common factor here. So we've got 2 to the x, and in the denominator we've got 2 to the x squared. That can be reduced, but the point is both of these are positive when x is positive. Actually, at all times, these are both positive, right? And what's left then is that we have 1 minus x times the natural log of 2. Okay? And what we learn is that this, of course, this portion right here is going to determine the sign of our derivative, this difference, because like we said, this is always greater than 0. Okay? And so this is going to be less than 0. This term is less than 0 when what? What's got to be true about x? Well, x has to be greater than 1 over the natural log of 2. And so this is kind of our definition of eventually, right? 1 over the natural log of 2 is, let's just say, this is definitely, this will definitely be satisfied if x is bigger than 3, we'll say. Okay? So you can check this, but eventually, though, your x can definitely be bigger than a constant, right? Because x is allowed to go all the way to infinity. And so this means that our function is eventually decreasing, and we can say check mark here. Okay? At this point, we're allowed to apply the alternating series test, and so what we have to check now is the limit as, again, n approaches infinity, n over 2 to the n. We know that this portion of our sequence, the non-alternating portion of our sequence, is positive and decreasing. The question is, does the limit equal 0? And we can do the same trick that we just did, right? Which is replace this function of n with a function of x, and actually compute the limit as x approaches infinity of x over 2 to the x. Okay? Now, as x approaches infinity, x, of course, approaches infinity, but 2 to the x also approaches infinity. And so this we get infinity over infinity, and of course this is screaming at us, hey, let's try L'Hopital's rule. Alright? So, let's try L'Hopital's rule. Remember, L'Hopital's rule says that we, in this circumstance, when we have an infinity over infinity, this is an indeterminate form, then we can compute the limit by actually taking the ratio of the derivatives, right? So we take the limit of the ratio of the derivatives. Derivative of x is 1. Notice this is not a quotient rule, right? This is just these straight derivatives here, which we've already computed in when we checked for decreasing, but we don't have to do a quotient rule. And what we find now is that this limit now has a 1 on top, right? So this is 1 over natural log of 2 times infinity. 1 over infinity in a limit is equal to 0. And this makes us happy because now we have our conclusion from our alternating series test, right? So by the alternating series test, what have we learned? That this series, n goes from 1 to infinity of n times cosine of n pi over 2 to the power n is convergent. We've checked all the criteria and it is convergent.